this is just the folder with the challenge unmodified from the contest. And as you can see, it has the setup contract. The setup contract, what it does is it imports a private Solidity like source code of like a contract, and then it deploys an instance of that contract, and then it just calls a function. It basically does some setup there. It buys some tokens. This function increases the balance of the setup contract in the challenge. So this is why initially this check will not pass, because this will be a non-zero balance. It also, because it sends 50 ETH to the contract, the balance of the challenge contract will also not be 0 in the beginning. And then because it's deployed by this contract, the owner will also be the setup contract in the beginning. So none of these 3 checks pass in the beginning. And then we just have to find a way to manipulate the challenge contract in a way that makes that happen. And we don't have the source code. So what do we have? Well, in the deploy compiled, we have the binary code. And so what we just did is we took that and just basically manually, right? This is the exact same one here in here. So we just basically recreated the setup contract just using the raw code. Does the exact same functionality. So this is how we get it on chain. And so how then did we solve it? Well, we just basically took a closer look at the code. We decompiled it with this nice tool here, and with a bunch of other tools as well. But this is, I think, the one that we used most kind of extensively. And then we just basically had a look. And so basically what it does, it gives you 2 outputs. This is like a high-level output. This is trying to make sense of what it basically got as raw code and tries to annotate things and whatever. And then at the very bottom of of this page, you also get the raw disassembly. And disassembly really is just opcode level kind of output. And so then basically the first thing to do was to kind of find like some anomaly, something where you can do things that you're not supposed to do. Because, well, I mean, very first thing what you could do is just try and find functions that do what you wanted to do, but all of those actually kind of do what they claim they do, right? So they're like the normal thing. So basically, in order to change the owner, you would normally have to call transfer ownership, but from the owner address, which is the setup, we can't do that, and so on. So there's nothing in there that has like any logic errors or something. So there's actually like some low-level thing going on that you have to find. And the name there was kind of like a hint, because it's all about jumps. So they kind of the whole point was there's like one hidden arbitrary jump in there that you can just use and do nice things with. And so basically, first, how can you find that jump? I'm not sure. Is that easy to see in here? I assume that might be easy. Not fully sure. It's here. This is where you could, looking through this is where you should have like a little light blinking. Error could not resolve jump destination. So this is kind of where the jump destination is just dynamically calculated. And so basically what we then just did is really like basically go into the raw code and just kind of figure out what's happening there. So if we kind of go to the raw code, just to the location, and then it just we kind of follow the code. Then we just basically reach this location. This is a jump. And as you can see, the annotation here is already kind of weird. It jumps to something, something, something. And in there is storage location 11, so 0B. So it kind of takes the, basically, I mean, the details are not that important, but the interesting thing is it just reads the jump destination from storage. So you can basically, if you can kind of fill in something into the storage field, then you can basically take this as a jumping off point and just jump wherever you want to jump. And not only that, but also you kind of know exactly how the stack layout will be at the time of the jump, because we annotated all of this. I can show you a copy of that. But basically, this I think it says here as well, right? The topmost stack element will be the value, basically the amount of ether, or the amount of Wei that you sent with the transaction. And so that's of course also an arbitrary value that you can set. So you kind of can jump to the storage location, but again, this maybe I should tell you now. The nice thing is there's this nice function, this handy little function up here, 0x27 whatever, and this all it does, it just lets you click our way through, it just lets you write an arbitrary value to this storage slot. So you can just basically you can fill in, and this is if I go back here and I just briefly show you the 2 transaction that I sent. So this was the first transaction that I sent, and then the top one was the second one. And so this is literally exactly right, calling this 27 function and setting 19fc. So basically we want to start our free execution jump to start at 195c. Why 195c, you might ask? Well, that is because well, I mean, I'm not sure like in what level of detail, but like maybe I'm in the flow, so I'll just go into a little bit more detail. So basically, as I was saying, right, we have our free jump here, but it has basically it on the stack it has like a return address. So if we jump into like some other subroutine and takes one element as a parameter, right? So if it takes like one argument, then it will interpret the message value as the argument. Then it will do whatever the subroutine is supposed to do, and then it will just jump back to our target destination. And so normally at that point, of course, our like arbitrary control flow would end, because then we are back in this like fixed control flow. But if we look at what does that location actually look like, well, it's just a jump destination that immediately jumps again. So what does immediately jump again mean? Well, it just jumps to another address that it just takes from the stack. So basically, if our subroutine that we jumped into with the arbitrary jump, if that returns at least one value, the return values are just the top stack elements, then it just basically jumps immediately again into wherever we want to go. And so the question is, of course, we kind of want to put interesting things on the stack. So how do we have the most control over what we put on the stack? Well, we just jump to a subroutine that reads things from call data, because then we can just send like an arbitrary amount of data with our function. So we just looked at which of these internal kind of subroutines return data that comes from call data, and we found this really nice one that actually is, if you look down this, I mean, as you might actually expect at this point, right? There are only 2 functions that have weird names, unknown names, and this is part of the second function. So I mean, kind of makes sense that they would kind of hide interesting functionality in there. But basically, so basically what we jump to is to this 19fc function. And if you kind of watched carefully, then you can see this is exactly what we wrote right here, right? So this is exactly the subroutine that we jump to. So it all kind of makes sense, hopefully, at least a little bit, maybe starting to make sense a little bit. So what does this function actually do? You can already see it takes one argument. Well, the thing that we control with the value that we send. And if you look at the exploit transaction, we send a value of 4. So the argument that we set that we give it like put in there here is basically like 4, and then it returns 4 return values. And so where do these return values come from? Well, long story short, it takes this argument that we give it, and this is temp 0, and it just takes that as an offset pointer to into the call data, which is perfect, because that means that we can basically read from starting at any position in call data. We can just read 4 words, so meaning kind of 128 bytes of data into these 4 variables, variable 4, 5, 6, and 7. This just read arbitrarily from call data, and then it just makes some checks. So we have some small constraints. The inner 2 variables are not allowed to be 0, but any other value is fine. Well, this third value also has like an upper limit, but the upper limit is kind of generous, so we don't really care. And the last value is not supposed to be below 27. But if we pass all of these checks, then basically it just returns these 4 values that it just read from call data just as is. And this is basically perfect, because then again the first one of those will be consumed as the next jump test after, right? And then we can jump somewhere. Now we have 3 values instead of only having control over 1 value and the destination. Now we have a destination and 3 values. Well, and because we are a little bit greedy, we thought, why have 3 values when you can have even more? And so where do we jump back? Well, how about just at the beginning of this function again? Because we can provide the offset of the call data. So this time around, we jump here and we don't provide a 4, but we want to basically, we already read the first 128 bytes. Well, I mean 128 plus 4, so we just provide 132 as offset. And then next time around, right, we just do that again. And so basically we do that a couple of times. In our case, we do that like 5 times total. And after the 5 times, of course, every time we also consume 2 stack items again, because we consume this destination and we consume the length. So we kind of every jump adds 2 stack items. So in the end, after 5 of these kind of iterations, we have 10 stack items that we control, plus the jump destination where we jump to. And this is perfect because we need exactly 10 plus address. So otherwise we would have basically had one more round or something, but this is exactly what we need. And so where do we then jump to? This is kind of the table where we planned everything out. It's a little bit confusing, so don't bother with the details for now. It suffices to say though that we this is the return data where we kind of jump out of the function. So we kind of jump to 102a. So let's see what 102a is all about. 102a, as you can see, is a function that does an store, so it stores something in storage. And as you can already kind of see hinted at, it kind of stores something in storage location 6. Storage location 6, I can maybe briefly show you the output of a different decompile tool that we had that kind of nicely mapped the storage location to kind of the values. So storage location 6 is the next owner. So how this next owner pattern works is usually only the owner is allowed to set the next owner, and then the next owner usually has to call accept ownership. So we basically do the first step of this ownership transfer by setting the next owner. And then I think at the very last step of our little exploit thingy, do we then accept ownership. And so for now, it's basically stuck in this pending state. But the nice thing is that this is a subroutine in itself. So as you can see, it doesn't have a hard-coded jump destination where then we would basically be caught in a fixed execution again, but it just jumps to a variable from stack again. And so basically, we only have to provide the new owner as a parameter. And in this case, it's a little bit confusing, but basically the very last element that we put on the stack in this whole kind of routine is the very first that is being read here. So this is kind of the new address that is, and that is exactly kind of the as you can see here, this is exactly the target address. So we will basically put the target address on stack into the right position. So then it's being set as the owner. And then, I mean, you can probably already guess how all of this is going to go. Basically, after this address, we basically do this routine, and then after we kind of jump to the next, then we do the variable jump again. That jumps to this time 191b, and of course it's getting a little bit repetitive, but we are almost done. So I think it's worth it. Maybe just stepping through the rest because I think it's just somewhat fun at least. So what does this thing do? Well, this time the important opcode is call. So as you might remember, again, one of the conditions was that the balance of the contract itself would be 0, but we sent in 50 ether, and we also sent in, crucially, and we forgot to account for that in the beginning, 4 extra way when we triggered the exploit, right? So we want to basically send out 50 ether plus 4 way, and we just do that by jumping into this subroutine. It's not, this is the start of the subroutine. This is a hard-coded jump, but I can just convince you in a second that it actually ends up giving us a dynamic jump opportunity again. But we jump to the beginning of this subroutine that includes a call, and crucially, as you can just see in the annotation here, or maybe even up here, if the call kind of the call takes the address from stack, so we can just say where it should call to, and it also takes the value from stack as well. So we can just specify exactly, and this is exactly what we do. So any address suffices because we just send the money out. We don't care where it goes, and we need basically the balance of the contract plus 4 as the argument, and then it just sends the thing out. And then just to very briefly convince you that we get a free jump again. So first we have basically a forced jump here. That jumps here basically, and then we have another jump here, and then we have a free jump. And this takes another one of our stack elements. So this takes in this case the next address that it's reading is this one, so 1563. And it jumps to 15663. So at this point, you might be wondering how far along are we in the process? Well, we have successfully solved this. We have partially solved this. We still have to accept. and we still have to set the balance to 0. So two left, basically, two down, two left. And so like we're kind of halfway there, and then now I think what we first do is we first set the balance to 0, like the balance of kind of the internal token balance also to 0. So let's see, we arrive here, and as you can see, it indeed does an S store. No, I think that's actually the let me see. Let me just see which one of that is. Which one that is. Oh no, yeah, that's so sorry, that's exactly right. So this, as you can see, that it has like an internal catch-up hash in there, and if you know anything about like if you know like something about like how Solidity internal mappings work, so basically, right, the kind of this the balance of that keeps track of who has how many tokens. That's basically a mapping, and mappings Solidity boils them down into basically like a catch-up based system to determine the storage slot in order to avoid collisions. And so this is kind of what the thing does. So it kind of calculates the address. And if we look at the annotation again, so then we can see that indeed at storage slot, right, this is the dynamically calculated, we rewrite an address that we just controlled. So this has to be a 0, of course. We want to empty the balance. And then what is this? Well, this is just basically stack element -3. So as you can see, stack element -3 is the setup address, the address of the setup contract, and that just becomes set to 0. The left ones, by the way, are just always used for control flow, and the right ones are the ones that we have full control over, basically. Okay, so now basically, and just to convince you again that like in the end, after it's done, we have like a dynamic jump to the stack element again. So we kind of just jump to this. So, and this is going to be the last thing. The last thing to do is just accept ownership. And so now we just do accept ownership. We just accept ownership, and then we will just need an exit to stop execution. So how do we accept ownership? Well, we just jump here, and all it does is just completely unconditionally, it just loads the value from storage slot 6 and instead fills it into storage slot 5, which is, if you look into this here again, storage slot 5 is just the owner. And so we can probably also see this annotated. So storage slot 5 basically is some masked version of storage slot 6. No checking, no nothing, it just trusts us here. And so, and it again has a dynamic jump to just whatever address we provide, which in this case will be this. And why do we provide one more address? We're already done. Well, we just have to not crash but now. And this is really easy if we can just jump here, because we just immediately stop. And so this is exactly what happened. We arrived at the stop, everything was done. And so this is how we kind of finally, very much like very long after the end of the competition, finally solved JOP. Jump-oriented programming was a fun challenge. Thanks for watching. I'll go offline now. Have a nice day. See you at the next competition.